Welcome to Study Loop.
So here we note that the acceleration vector is constant, so we can use equations 313a, 313b. We also know that the initial velocity vector is going to be 0 meters per second. The initial displacement vector is also 0 meters. So we can say that for part A, v final would be equal to v initial plus a vector at. This would equal 4.0t times I hat plus 3.0t times j hat meters per second. And we can say that v sub x equals 4.0t meters per second. V sub y would equal 3.0t meters per second. For part B, we can say that the magnitude of the velocity vector would then be equal to the square root of v sub x squared plus v sub y squared. Let's solve. So this would be equal to the square root of 4.0t meters per second quantity squared plus 3.0t meters per second quantity squared. Take the square root once again, and then this is equaling 5.0t meters per second. So that would be the magnitude of the velocity vector. And then for C, when we want to find the final displacement, this would be equal to the initial displacement, which we know to be 0, plus v initial t plus 1/2 times the acceleration vector times t squared. This term becomes 0 because the initial velocity is 0 meters per second. This term becomes 0 because the initial displacement is 0 meters. And so this is going to equal 2.0 t squared I hat plus 1.5 t squared j hat meters. And at this point, we can solve for D. We want to solve for the x component of the velocity after t equals 2.0 seconds. So this would equal 8.0 meters per second. The y component of the velocity after t equals 2.0 seconds. This would equal 6.0 meters per second. And then the magnitude after t equals 2.00 seconds. This would, of course, equal 10.0 meters per second. We can say that the displacement at t equals 2.00 seconds would be equal to 8.0 I plus 6.0 j meters. That is the end of the solution. Thank you for watching.